In the name of Allah Almighty, the Beneficent, the Merciful, welcome to PH 101 Lab FES GIKI. So our today's experiment, our fourth experiment is about the ballistic pendulum. So in order to proceed, we must know the prerequisites required for this experiment. So the first one is the conservation of momentum. So first we need to know about what is momentum. So actually, momentum, we can say that it is the quantity of motion in a body, or simply if a body of mass m is moving with some velocity, if a body of mass m is moving with some velocity, then we can say that it has some momentum. So simply if I say that a body of mass m 50 kilograms is moving with velocity 500 meter per second. So its momentum will be 50 into 500. And the unit will be kg meter per second. So this will be actually its momentum. So when you multiply 50 into 500, you will get the momentum. So this is simply the concept of momentum. What is momentum? So now we will move towards the conservation of momentum. So in the previous lecture, we discussed the conservation of energy. So all the conservation laws, for example, the conservation of energy, the conservation of momentum, you should be aware of this, that it is only valid for isolated system. When the system is free from external forces, when there are no environmental effects, then we can say that the statement of the conservation of momentum is the total momentum, which is P is equal to mv, before and after the collision remains conserved. So this is the simple statement of the conservation of momentum. So what is this term collision? What is collision? So simply, in order to understand collision, it is defined as it is an event in which two or more bodies exert forces on each other when comes in contact in a relatively short time. So this is a very simple example. This figure shows a very simple example of this of such an event which we call the collision. So let's say I have a steel ball of mass ma, and it is moving in this direction. So it has a velocity of va and it has mass of ma. So its momentum will be ma va. Now there is another ball and it is moving in this direction and it has a mass of mb and its velocity is vb. So its momentum will be mb multiplied with vb. Now when these two bodies will approach, when these two bodies will approach here, when these two bodies reach here, they will come in contact. So if these are, let's say, hard steel balls, or let's say these are mud balls, or so when these two bodies come in contact, what will happen? It has some momentum. It has some momentum. So this body will exert some force Fa on this mb in this direction, and this body will exert some force Fb in this direction. So which body will have higher velocity, which body will have lower velocity, which body will become at rest, and which body will start moving with different velocity. So there are different types, and we are not going to discuss them. So you should have a very basic idea of collision. It's an event in which two or more bodies collide and they exert forces on each other. So this is a very simple explanation of collision. And for any isolated system, the total momentum before the collision and after the collision will remain conserved. Now, there you should know about the types of collision briefly. So the first one is the elastic collision and the second one is the inelastic collision. And there are perfectly elastic collisions, but we are not going to discuss them. The first one is the elastic collision. So in elastic collision, both the momentum and the kinetic energy is conserved. So if a system is moving, we know that if a system is moving, so it has some kinetic energy, half mv square. So if it has initial kinetic energy, it will be miv square and mass is constant. So when we are dealing with the case of elastic collision, both the momentum and kinetic energy will be conserved, will remain constant. Both momentum and kinetic energy is conserved. And the example we can take is, this is not perfectly elastic, but we can assume that if the collision of two hard steel balls, so if we have hard steel balls and these hard steel balls collide, so we can consider them to be elastic collision, which is not perfectly elastic, but we can consider them as an example of elastic collision. And in inelastic collision, which is the part of this experiment, which we will be discussing in our experimental demonstration, and also in the theories and calculation, we will be discussing the apparatus for the ballistic pendulum. So in inelastic collision, we have only momentum that is conserved. So it means that if the momentum is conserved, the kinetic energy is not conserved in case of inelastic collision. So we can say that what is the example of, simple example of the inelastic collision is when two cars collide. So the initial momentum before the collision and the final momentum after the collision remains conserved in an inelastic collision, but the kinetic energies are not conserved. So the initial kinetic energies is not equal to final kinetic energies. So what happens to the kinetic energies? So the kinetic energies appears in the form of thermal energy. Either it is thermal energy, heat energy, or it may be sound energy. So what happens to the kinetic energy if the initial kinetic energies is not equal to the final kinetic energies? We will shortly write its mathematical form, how we write the initial and final momentum. Don't worry. Appears in the form of thermal or sound energy. So we can say that it's an inelastic collision. Or sometimes the kinetic energy is used in the deformation of a body. When two cars collide, so both the cars deform. So some energy is required to deform the, let's say, deform the cars. So that energy, the kinetic energy, is used there. So we can simply say that it is an example of inelastic collision. So in inelastic collision, only momentum is conserved. And in elastic collision, both momentum and kinetic energies are conserved. So you should be clear about these things. So let's write a mathematical form for the conservation of momentum. So let's say we have two bodies. Again, the same example, it's moving in this direction and a body of mass mv is moving in this direction. So before collision, when they strike each other, what will be the momentum? So we can call this the initial momentums and initial momenta and initial kinetic energies. And when they collide, what will be their final momentum and final kinetic energies? So what will happen? Let's say this is body of mass MAVA. So the initial velocity, I can write it like MAVAI. This I represents the initial momentum of this ball. And let's say for this body MBVBI. So this is just for understanding how we write the equations. So this is the total initial momentum of these balls. So when they collide, this will be equal to, after the collision, the momentum will be equal to MAVBF. F represents the final momentum, I represents the, in the subscript, represents the initial momentum, plus MBVB, the final momentum of the second ball, F. So this is the representation of the conservation of momentum. The initial momentum is equal to the final momentum. Similarly, for kinetic energies, kinetic energy, momentum is equal to P is equal to mv, simple, mass into velocity, and the kinetic energy is equal to half m times v squared. So this is actually the kinetic energy. So the initial kinetic energy will be half ma, because for a body of mass ma, so its mass will be ma vai whole square, because mass remains the constant. So we cannot write I here, not here, also not here. So we will write I with the velocity only. The velocity changes after the collision, plus half mb vb I square. The initial kinetic energies, the sum of the initial kinetic energies before the collision, is equal to final kinetic energies ma va f square, plus half mb vb f whole square. So these represents the kinetic energies conservation and the the kinetic energies conservation and momentum conservation. So if it is in elastic collision, so this is for the case of elastic collision. Initial and final is same, and the initial kinetic energies and final kinetic energies are same. So we can say that it's elastic collision. But for our case, it's not elastic collision. The initial kinetic energies will not be equal to the final kinetic energies, and we will find the percentage lost in the kinetic energies. And what happened to the kinetic energies? The kinetic energies is used, or it is transformed into some other energy, as we discussed, in the form of thermal energy, in the form of heat energy, or it is used for the deformation of the bodies. So you should be clear about these things. So this is simply the mathematical form of the conservation of momentum. Now we will move towards the ballistic pendulum. So what is a ballistic pendulum? As you know that a pendulum is like, let's say this is a pendulum. It contains a thread or a string connected with a bob. So when I apply certain force in this direction on this bob of mass m, it is fixed from here. Let's say the length of the string from the center of the bob is L. So when I disturb this ball or this bob, it will come here. So when I release the bob at point C, let's say, or at point B, this is the initial point at the mean position. So when I disturb this mass of bob of mass m, let's say bob of mass m from the mean position in this direction by applying certain force, and then I release the bob here, so it will move to its mean position back. So we know that because of the influence of gravity. So this is actually a pendulum. It represents we call this a pendulum. It's a pendulum. So what is a ballistic pendulum? So we will be using a projectile launcher, as we discussed in our experiment number 1, the conservation of energy. And next to the projectile launcher, there will be a pendulum. So we will insert the ball in the projectile launcher, then we will cock it at the medium or the medium or the short range, and then we will fire the ball. When it hits the pendulum, the pendulum will move. So we say that it's a ballistic pendulum. We are applying force on the pendulum, or let's say the pendulum moves because when we fire the ball and the ball hits the pendulum. So we will be discussing this in our experimental section. Now the apparatus required for our experiment is the projectile launcher, the projectile catcher, as you can see in the figure, the table clamp which is used to fix the projectile launcher and the whole setup on the table. A steel ball will be we will need a steel ball of mass 61.28 grams, and the projectile mass is 200. The projectile catcher mass is 235 grams. So the ballistic pendulum, we will need a pendulum, we will need a meter stick, carbon paper and white paper for this experiment. So what is the purpose or the objective of this experiment? The objective of this experiment is to calculate the muzzle velocity of the ball. So what is a muzzle velocity? Let's say if this is a projectile launcher or a gun, so it has a barrel. Let's say this is the barrel of the projectile launcher. So let's say here is the ball, right? And we, let's say, as we did it in our previous experiment, as we fire the ball, it leaves the barrel at the open end of the barrel. At the instant it leaves the barrel, it has some velocity V0. At the instant it leaves the barrel, it has some velocity V0, which we call the muzzle velocity. Or we can say that the initial velocity of the ball when it leaves the barrel. So it's the muzzle velocity. Now let's understand the setup, the apparatus which we will be using for our experiment, and which we will be demonstrating in our next part, in our next section. So this is actually a simple setup of a projectile launcher, or we can say the ballistic pendulum. There is a projectile launcher with a pendulum. So what happens? A projectile launcher with a fixed distance from the floor surface, as we discussed, its maximum height of the ball is y from the surface of the floor. And here we have a pendulum. It's a pendulum. It's like suspended pendulum right next to the projectile launcher, and it has some mass of 235 grams, mass of the catcher. So I can write MC. If I write MB, so we can say that mass of the ball. So this is actually the ball. This is the ball needed for this experiment. We will be using this. Its mass is about 61.28 grams. So we'll be using this for our experiment. So this is MC, MC for the mass of the catcher, MC is for the mass of the catcher, and MB is the mass of the ball. Here we have a degree scale, and it's calibrated, and there is a pointer. You can say it's a pointer. What happens simply? So when we place the ball and lock it at long range, and then we pull the thread. So what happens? The ball will leave this barrel with a muzzle velocity, as we know. Now here comes the collision. When it will leave the barrel, it will strike this catcher. So it's called catcher because it catches the ball. It has the ability, it has a space that catches this steel ball. So when it leaves the projectile launcher, it goes into the catcher. And here it is the collision. This is an event of collision. So what will happen? We have initial momentum and final momentum, and similarly we have initial kinetic energy and final kinetic energy of the ball and the catcher. So let's say here we have the steel ball, let's say of mass MB, placed inside this projectile launcher. At the instant I pull this thread, the ball will move with a certain velocity, a muzzle velocity. It will strike this catcher, and then it will stuck into this catcher, and it will move with certain velocity. Definitely when it will stuck into this catcher, this pendulum will move a little high. This pendulum will move a little high. Definitely some velocity is imparted to this catcher. So the pendulum will move. Definitely the pendulum will move. And what will happen is the pendulum moves. We have a degree scale. And with this pendulum there is a pointer. So how high it moves, we will record the angle. Let's say we say this is 25 degrees. Let's say we say it's 30 degrees. So it depends. So if you lock the ball at short range, it will move a little high. And if you lock the ball at long range, it will move a little more. So we will have to calculate the height. Its mean position is here. So when the pendulum moves, let's say this is the pendulum, and it moves like this, completing an oscillation. Let's say it moves here. So from here to here, it covers some height, and this is required for the potential energy. So simply it's very simple. Again, we have a projectile launcher. We cooked the ball at medium range or at long range. Here we have a pendulum with a catcher. The catcher is used to catch the ball. So when we pull the thread of the projectile launcher, the ball will leave the barrel of the projectile launcher with a muzzle velocity, which we have to calculate, and it's the objective of our experiment. And we will be studying the momentum of conservation of momentum. So we have initial kinetic energy of the ball, and initially the catcher is at rest, so its initial velocity will be 0. At the instant it strikes the ball will go inside the catcher, it will catch the ball, and then with the ball it will move a little high. So when it will move, it will make certain angle theta, and this theta can be determined from this degree scale. So we have to note that theta down. The ball has mass of mb, and its initial velocity is v0. Let's say you can represent it with Vm, muzzle velocity. For your ease, I can write it V0, muzzle velocity. I will write it here. V0 is for the muzzle. So I can write it muzzle velocity in meter per second. So this is the initial kinetic energy. It is the initial momentum mb V0. And what is the momentum initially of the catcher? 0, because it is at rest. If it has some velocity, it will have some momentum. So initially we have only the momentum of the ball with the muzzle velocity in it. Now this is the initial case. Now when this ball will strike the catcher, let's say this is the ball, and here it's the catcher. It contains some space. So when the ball strikes the catcher, it moves into the catcher, and the ball, what happens? Next, the ball is stuck here inside the catcher. It's called catcher because it catches the ball. So now we have what happened. Now this catcher is connected with the pendulum. It will move. Definitely it will move with a certain angle. So when it will move, now what is the mass of this catcher? Now the mass of the catcher including the mass of the ball. So the catcher mass is now the mass of the ball, because the ball is stuck inside the catcher. The mass of the ball and the mass of the catcher. This is the mass of the catcher and this is mass of the ball. So we will have total mass of the catcher. And when it will move after the collision, it will move after the collision. So what will happen? I can say that its velocity is v. It's just a representation. I am using v, the velocity after the collision. I am using v, velocity after the collision. So here comes the collision, velocity after the collision. And it's an example of inelastic collision, because here some kinetic energy, you can say it's converted into sound energy or thermal energy. And we have also to calculate the percentage loss in the kinetic energies, the initial kinetic energy and the final kinetic energy, which we will be doing shortly. So this is just the simple setup, and definitely we will be demonstrating it in our next part, and you will have a better idea how to perform this experiment. So keep in mind, initially this was the momentum, initial momentum, and this is now the final momentum. So keep in mind, you have to include the mass of the ball when it is stuck inside the catcher, and then it will move, and when the pendulum moves, it will come back to its mean position. Let's say its mean position is here, so it will come back to its mean position. And what will happen? As it moves, this pointer will move with the pendulum. So you can say from the degree scale here, by looking onto the degree scale, you can say whether the angle is 25 degree or the angle is 30 degree. So if you see, it's making a right angle triangle. So here is the theta, basic mathematics. Right in front of theta, always keep in mind, always right in front of the theta, we have the sine component, sine theta, and the side which makes an angle of 90 degrees with the base, it's always the cos of cos theta, and this is the hypotenuse, right? This is the hypotenuse. So there are two things you should know. The first one is the RC, and the second one is RB. The first one is RC and the second one is RB. So keep in mind, we will be demonstrating it in our experiment, but keep in mind, let's say this is the length of the pendulum. So we have the catcher, here is the catcher, its center of mass is here, and let's say here is the ball is here, let's say its center of mass is here. This is the pendulum. Here at the end of the pendulum we have the catcher. Inside the catcher, let's say it's the ball. So from this point, from the fixed position, from here to the center of mass of the catcher, this distance is called as the RC. It's the length simply. And this distance from the center, from this fixed position to the center of mass of this ball is known as the RB. So there are two distances. One is the distance from the top, from the fixed position from here to the center of mass of this catcher. So it's RC. And RB is the distance from this fixed position to the center of mass of the ball. This is RB. So you have to keep in mind how to, and we can simply using a meter stick. So using a meter stick, this is a meter rod. Using a meter rod, we can calculate by placing it here, and we can say, let's say this is this much centimeter and this is this much centimeter. So there will be a little difference between RC and RB. So this RB is calculated from this to this. Keep in mind. Now another thing is, let's understand the maximum height. So if you're talking about the potential energy, you should be talking about the position simply. So when it moves, when the pendulum moves, so let's say its mean position. Let's draw it. Let's say this is the catcher with the ball. The catcher catches the ball. The catcher catches the ball, and let's say initially when the ball strikes the catcher and it moves, making a certain angle theta. So let's say its position is here now after the collision. So it's making a certain angle. Let's say this is a position. So it's the mean position. So from this reference level, how high is the catcher? How high the catcher moves? So this is actually h. We need this h. This is the h. And how to calculate this h? Simply, if you see, this is making a right angle triangle, as we discussed. This is making a right angle triangle. So always keep in mind, write it front of the theta. So here is the angle theta from here. Write it front of the theta. The side is known as the sine side, sine of theta. And the length of the pendulum is, what is the length of the pendulum? This is from here to here. The length of the pendulum is RC. And the length of the pendulum is, let's say this is the length of the pendulum. From here to the catcher's end, the length of the pendulum is RC. And we know that how to find RC. Right to the center of mass of the catcher. So if this is RC, this component will be RC sine of theta. And this component, keep in mind, this component will be RC cos of theta. The side which makes an angle of 90 degrees with the side in front of the theta. So if it's perpendicular, it will be the base. So I can find this h simply. I can find this h if this is the complete length. The length of the pendulum is RC from here to here. So the length of the pendulum is from this position to this position is RC. Right? So when it moves here, it covers some height h, this h. How to calculate this h? Simply, if we know this total distance RC, which we can calculate, and if I subtract r cos theta from this RC, r cos theta from this RC, I will get this h. If I subtract r cos theta from RC, I will get this height h. So how to calculate? So we know that this h is equal to this height of the catcher or the pendulum is equal to RC minus RC cos of theta. So taking common RC, h is equal to RC 1 minus cosine of theta or cos of theta. So we can find theta from looking onto the degree scale here. The pointer will tell us whether the angle is 25 degrees, it's 50 degrees, and when you will put the angle here, RC you have calculated using the meter stick, you will get the h, you will get the value of h. Now let's discuss as the ball moves here. Initially, when it moves, the pendulum moves initially, so it has initially the kinetic energy. So when it reaches here, it stops for a while, and now it has covered some height h. Now at this position B, it has now some potential energy, and initially it was having kinetic energy. So at this position B, I can say that the kinetic energy of the ball is converted. The kinetic energy of the ball is converted into the potential energy P dot E. And so the kinetic energy is half mv square. And now I am writing v square, and we are using v after the collision. And definitely this is for the case after the collision. The body has moved a distance h, and this is right after the collision. So I will not be using here v naught. You should not be confused in v naught. You should be aware of we are using v naught for the muzzle velocity. We are using v for the velocity of the collision. So you should be aware. mc is for the mass of the catcher, mv is for the mass of the ball, and what else? rc is for the distance of the catcher right to the center of the catcher, and RB is the distance from this fixed position to the center of the mass of the ball. So you should be clear about these things, and we have calculated this from the right angle triangle. By applying or by looking into the figure, we can just pick our required things. So this is half mv square, and this is equal to mgh. At this position, when it will be here, the kinetic energy will be converted into the potential energy, definitely, and this mass will cancel with this mass. And if you shift this to there, shift this to the right side, so we will get v square is equal to 2gh. Now if we take the square root both sides, v is equal to under root 2gh. We will get under root 2gh. So this is actually the velocity after the collision. Keep in mind, this is the velocity after the collision, and you can simply find it if you know the height. If you know the height the pendulum has covered, and we know the value of g is 9.8 meter per second square, keeping and using same set of units, 2 is a constant, and if you take the square root, you will get the velocity after the collision. So this was for the conservation of kinetic energy, and we have also discussed the conservation of momentum case. So this is basically the example of inelastic collision here. Some kinetic energy is lost in the form of thermal energy, and when it strikes the, let's say, the catcher, so we can say that some energy is converted into sound energy. We will hear a sound, so it's converted into sound energy. Now, as we discussed, this for the conservation of momentum, that initially before the collision, the ball mass was mv, and its muzzle velocity, right, it leaves the barrel before the collision, its velocity was v0, and it's equal to, now when it strikes the catcher, it moves into the catcher, and the catcher catches it, and now the catcher is moving with the ball. So we can say that its velocity is now, its momentum is mb plus mc, mass of the ball and mass of the catcher, with velocity v. This is the velocity before the collision, right? It leaves the barrel, and when it strikes the catcher, the ball is moving with the catcher with the velocity v. So this is the conservation of momentum. So this is the purpose. You should be aware of the purpose. We are using the conservation of momentum to calculate the muzzle velocity v0. So simply. So now let's play with this equation. I have calculated the velocity after the collision. So I substitute this value. Let's say this is our equation 1 and this is our equation 2. Let's put this equation 1 into equation 2. What we will get? We will get mb v0, the muzzle velocity, is equal to mb plus mc v. So in place of v, instead of v, we can put under root 2gh, under the root square root 2gh. Now dividing both sides by the mb, I need to calculate this v0. So I will get v0 is equal to 1 over mb, or simply mb plus mc divided by mb under root 2gh. So this is known as the calculated muzzle velocity. This is called the calculated, we call this the calculated muzzle velocity. So what will be required? We will need the mass of the ball, the mass of the catcher, the gravity value 9.8 meter, the gravitational acceleration 9.8 meter per second square, and h. And we have to calculate h by different trials. We will be discussing a table, and in that table we will calculate h for different trials, and then we will take the average. So actually this h is the average value. Keep in mind, this h is the average value. This h is average. H average is actually h. Keep in mind, you will not do it for just a single trial. So this is the calculated muzzle velocity. So this experiment has two parts. The first part is the muzzle velocity, and the second part is the muzzle velocity has two parts. First we will say muzzle velocity part 1, and then we will say calculated muzzle velocity. So what it means? Simply, in our previous projectile launcher experiment, we calculated the horizontal distance, x dash plus x average, and we got a horizontal distance, total distance, average distance. And by dividing that average distance by the time of flight, we have calculated using this t is equal to, time of flight is equal to 2y by g. So we calculated the time of flight in the first experiment, experiment number 1. And from there we got v is equal to x. We got the x, the total horizontal distance, and how to calculate it? We have already discussed that in our first experiment. So you can check it out. V is equal to x by t. So if you know the horizontal distance, the total horizontal distance, we were taking trials. Let's say for first trial, for second trial, when the ball leaves the barrel, for initial, then we calculated its average value, and using that average value, we add it with the horizontal distance. In that we added with the horizontal distance x, and we got this x value from there. So we will get the v. So actually that v was v naught. That what was that v? What we discussed in our first experiment was the muzzle velocity. Why? Because we know when the ball leaves the barrel, we call it the muzzle velocity. When the ball was leaving the projectile launcher, the barrel of the projectile launcher, it was having certain muzzle velocity, and actually this will gives us the muzzle velocity. This will gives us the muzzle velocity. So simply you have to repeat this experiment. You have to repeat experiment number 1 first for comparison. If you are using the calculated muzzle velocity, you have to use this equation. And this is our part 1 muzzle velocity from experiment number 1. Using the same setup, we will take 10 trials. We will calculate y from the fixed distance. So we can calculate it from here. What is the distance? This is y. We will find this t. Then we will place it here. Then we will put it here. We will find the velocity. And this velocity is actually the velocity of the ball when it leaves the projectile launcher. So we will call this the muzzle velocity. But part 1. This is our part 1 muzzle velocity. So we know this from our previous experiment. And if you are confused, you can go and check it out. The calculations are so far very easy, and I have made it very simple for you to understand it. Basically, this experiment has 2 parts. In the first part, we will repeat simply the first experiment, to study the conservation of energy via the projectile launcher. So we have discussed it, but I will again repeat that a little bit. We will draw its tables, and then you will have to fill it. And the second part is we will be discussing the ballistic pendulum as well. So in the first part, what we will have to do, you will not be using this pendulum in the first part. What we will do, we will move this pendulum here, and when you move this pendulum here, it will be locked. It will get locked. It will get locked here. So you will keep it here. Again, you will keep. We have discussed this in our previous experiment, but let me repeat. You will keep a paper, white paper. Then at the top, you will place a white paper right in front of the projectile launcher. Its distance from the table surface is y. The distance from this projectile launcher plus position, the distance from the plus symbol to this page was x dash. We know that. And when the projectile strikes on the top of the white paper, we have a carbon paper. So for the first case, we will clock the ball again, we will fire the ball. This is our first trial, second trial, third trial. Then we will calculate distances of these dots from the edge of the paper, and then we will take the average. Let's say the first trial, the distance of the first dot is x1, the distance of the second dot is x2. So we will add these dots distances from the edge of the paper. We have discussed this for 10 trials, x4, and then we will divide it by 10 to get x average, and then we will add this x average with the distance, fixed horizontal distance from this plus symbol to the edge of the paper, x dash, to get x, right? And we will put this x here, x by t. And how to calculate t? We have discussed this, the total time of flight of the ball. So how much time is required for the ball? So 2y by g. Y you can calculate it from here, from this. You have to calculate y for this experiment, keep in mind. So the rest is the same. You will have a plus symbol and you will get a value of y. Now when you calculate this value v0, this will be our muzzle velocity. This will be our part 1 muzzle velocity. Keep in mind, muzzle velocity part 1. Right? Then we will discuss the ballistic pendulum. We have already discussed the ballistic pendulum, the equation for the ballistic pendulum. That was v0. For the second part, v0 was mv plus mc. We have calculated. We have also discussed the second part under root 2gh using the conservation of momentum. So this is the calculated muzzle velocity, and you will have to calculate it in the second part of this experiment. Calculated muzzle velocity. This is the calculated muzzle velocity. Keep in mind. So let me repeat the first part very briefly. This was, as we discussed in our first experiment, this was the trials table. Trial 1, you have to record the distance. For trial 2, for trial 3, 4, 5, 6, up to 10 trials. And then you will take the average. This was the distance from the edge of the paper to the first dot, let's say. So we will call this 1. Then the second dot, third, fourth, 5, 6, 7, 8, 9, 10. Then we will take the average. We will get xavg in the subscript. So you will get an average value. Then we will add this average value with the fixed horizontal distance. As we discussed x dash, we will get x. From this equation, we will get time of flight, sorry. We will put this in this equation, and we will get the muzzle velocity, simply muzzle velocity part 1. This is the muzzle velocity, and this is for part 1. So it's very simple. Part 1 is clear. Now let's move to the second part, that is the ballistic pendulum. So in the second part, we are having some tables and we have to fill them. How to fill the first table? Let's say this is our first table. This is our table 1. This is our table 2. Now how to fill this table? Initially, as we discussed, when the pendulum moves, there will be a degree scale, and from here there will be a pointer, and this pointer will tell you the value of theta. So when you get the value of theta, we know that H is equal to RC 1 minus cos of theta. So we discussed this RC or RCM, you can say center for the center of mass, or I'm using C. So if you know the value of theta, we will have already calculated the value of RC, which we will be discussing in our experimental section. We will be using a meter stick and we will calculate this RC. So when you know the value of theta, let's say our theta value is 25 degree. You will put the value of theta here, 25 degrees. You will have already calculated the value of RC, and you will get H. Let's say I call this H1. And again you will took the ball let's say at long range. You can do it for short range, for small range, and for long range. So you will get 3 tables. There is no restriction. So let's say I am locking the ball at 25 degree again. I am locking the ball at long range, and now the degree scale tells that the angle is now 25.5 degrees. So it will be H2. Now the angle is again, let's say 25.9 degrees. So it will be H3, and similarly for the third case we will get H4. Now you will take the average of this, H1 plus H2 plus H3 plus H4, divide by 4, you will get a single H average. Let's call this H average as H. And you will need this H in our calculations. Here, you have calculated the average value of H using this table. So you will put the value of H in this table. Using this table, you have calculated the value of H, you will put it here. Now let's move. Calculated muzzle velocity. We have discussed it and now we are clear that the calculated muzzle velocity as we have derived it is V naught is equal to mv plus mc divided by mb under the root 2gh. Again this h is calculated from here, h. And when you calculate this h, you will put it here. You know mc, mb, mass of the catcher, mass of the ball, and you will get the calculated muzzle velocity. You will put the value here. Now the muzzle velocity from the part 1. So this is the muzzle velocity from part 1. The trials part 1, 2, 3, 4. You have to take some trials, then the average. We have discussed it. So you will get the muzzle velocity for part 1. And now you have to write the velocity after the collision. So the velocity after the collision was simply under the root 2gh. We have also derived it. V is equal to under root 2gh. So you can also calculate this value. If someone asks you what is the velocity of the ball after the collision, so you should know the value. V is equal to under root 2gh. Using this equation, you will calculate the velocity after the collision. Now, what will be the percentage difference? And the percentage difference will be between the calculated muzzle velocity and the muzzle velocity. So simply, muzzle velocity part 1 minus calculated muzzle velocity divided by muzzle velocity part 1 multiplied with 100. So you will get the percentage difference, and it should be less than 10%. It should be less than 10%. Now this is required for the case of muzzle velocity. Now we have to calculate, this is very important, you have to calculate the percentage loss in the kinetic energy. So how to calculate the percentage loss in the kinetic energy? It's very simple. Kinetic energy before minus kinetic energy after collision, and then divide this value by the kinetic energy before collision multiplied with the 100%. So kinetic energy before collision is mv muzzle velocity. You have to use the muzzle velocity. And after the collision, when it's stuck inside the catcher, the mass becomes the mass of the ball as well as the mass of the mass is now the sum of the masses, mass of the ball and the mass of the catcher. This is after the collision, kinetic energy after collision. And this is before collision. So you can simply calculate the percentage loss in the kinetic energy. Now let's discuss the approximate method and the exact method to calculate the muzzle velocity. So actually the approximate method is exactly the same as the calculated muzzle velocity. So we can simply calculate it from here when the pendulum moves from its initial position, mean position, to some other position, let's say B, by covering a vertical distance of h. By covering a vertical distance of h. So we say that when the catcher moves with the ball, so its kinetic energy is half mv plus mc v square is equal to its potential energy here. When it will move here, it will cover h, and at point B it will come at rest. At point B it will be at rest for a while. So its potential kinetic energy will be converted into potential energy, and again the mass will be the mass of the ball plus mass of the catcher into h. GH, sorry, it will be GH. So this will cancel out with this, and we will get V is equal to under root 2GH. Now we have, from the momentum conservation, we know that we have calculated this before. We will get V naught is equal to mb plus mc divided by mv, and instead of velocity after the collision, we will put this value here, so we will get under root 2gh. So this is actually, we will get a muzzle velocity using the approximate method, or we can say it's the calculated muzzle velocity. So this is the approximate method. Now what is the exact method to calculate the muzzle velocity? Actually, when we talk about, let's say this is the pendulum. So when the pendulum moves, so if this pendulum is in motion, let's say, right, like this, if this pendulum is oscillating, let's say, so it is covering some displacement theta, angular displacement. It's covering some angular displacement theta. So we can say that we can involve here some terms, that is the inertia. We can also involve terms inertia, angular momentum, angular frequency. So we can involve these terms here. If we see it's oscillating, so we can involve I, L and omega here. Also we can involve the time period of the simple pendulum, which we will be discussing shortly. So there are two kinetic energies. One is the kinetic energy linear, or we can say not for the rotational case. The linear kinetic energy is half mv square. Now we have equation v is equal to r omega. The linear velocity or the tangential velocity is related with the angular velocity. V is equal to r omega. So from here, v square will be r square omega square. It will be r square omega square. So kinetic energy is equal to half m. Instead of v, I can write r square omega square. Now we can say that I is equal to mr square. This is the inertia. Inertia is the property of body to resist any change in its state. Whether it's at rest, you want to disturb its state, it will try to maintain it simply. If it's moving and you want to stop it, it will try to maintain its state. So this is inertia. I will put the value of v here. So mr square will be replaced by I. So kinetic energy is equal to half I omega square. Now let's play with the equation. Multiplying and dividing this right side by I. So I will be the inertia, I divided by I. So we will get I square. The kinetic energy is equal to half I square omega square divided by I. Now we have another term, L is equal to I omega. Now the angular momentum is equal to the inertia multiplied with the angular velocity. So angular momentum is always when something is rotating. Let's say if something is rotating, there will be angular momentum and there will be angular velocity. So if we are dealing with the rotational case, we will be using the rotational kinetic energy. Kinetic energy rotational is I omega square. Now from here I can replace this by L square. So if this is squared, I can say this is L squared. Kinetic energy is equal to half L squared divided by I. Let's calculate I from here. So this will be 2I is equal to, if I shift this 2I here, multiplied with kinetic energy is equal to L squared. Now taking the square root both sides, L is equal to under the root 2I into K dot E. This is the kinetic energy. Now let's move ahead. So this is actually the kinetic energy after the collision. So what will happen when the pendulum moves to a position from this point A mean position to this position? It will have now potential energy. Here it was having kinetic energy and now it has potential energy. So the kinetic energy will be equal to the potential energy here, and this potential energy will include the mass of ball and catcher into GH. So the kinetic energy is converted into mb plus mc into GH. So I will replace this kinetic energy by this value simply. So we will get L is equal to under root 2I into mb plus mc GH under the root. So this will be the angular momentum. Now I can also replace this L by, we know this L is equal to R into linear momentum, where P is the linear momentum. Now L is equal to R, M is M, and momentum is mv, so we can write it mv. Let's replace this R by RB, and the mass will be replaced by mb, and V will be replaced by V naught. From here, this is the radius, this is the distance to the center of the ball, this is the mass of the ball, and this will be the muzzle velocity. So put this value here. we will get RBMB V naught is equal to under root 2I MB plus MC GH, and this H is the average value, keep in mind. Now divide both sides by RB MB. V naught is the muzzle velocity and this is the exact value, 2I MB plus MC GH divided by RB MB. So this is the exact value for the muzzle velocity. This is the exact method using this. But here is a problem, there's a problem. We know the value of RB, MB, GH, H, but we don't know the value of inertia I. So how to calculate this value I? Now to find the value of inertia for this equation, inertia, you have to keep in mind that the frequency in such a case is of the simple pendulum when we involve the inertia term is equal to mgl, length of the string or length of that rod of the pendulum. So I am calling this as RC, the length of the rod, divided by the inertia. Now we know that omega is equal to 2 pi f. The angular frequency is related with the linear frequency. So frequency is 1 over time period. So I replace f by 1 over t. Omega is now 2 pi by t, put it here. So I will get 2 pi by t is equal to under root mgrc divided by I. Now squaring both sides, we will get 4 pi square divided by t square, which is the time period, is equal to m. Now the m is because we are discussing the case after the collision, so m will be replaced by the mass of the ball plus the mass of the catcher into grc divided by, this will cancel out with this, divided by the inertia. Now simply you can play with this equation to calculate the value of inertia. So I will shift this I here, I will get I is equal to, and I will shift this t there. So I will get MB plus MC. The final version of the equation will be GRC into t square. T will be shifted here, t will be shifted there, t square divided by 4 pi square. Now this is the final equation to calculate the inertia. Keep in mind, using this equation you will calculate the inertia. You know the mass of the ball, the mass of the catcher, the length of the rod of the pendulum. G is the gravitational acceleration, time period. So normally the time period is actually 1.09 seconds. But if you want to calculate the time period, it's very simple. T is equal to 2 pi under the root L by G. So L is RC divided by G. So either the instructors will tell you the value of the time period for the pendulum. You don't need to calculate. They will tell you. But if you are not, if you don't know the value of the time period, you can use this equation, the time period. So 2 pi is constant. RC is the length of the pendulum divided by the G. So if you know the RC, the length of the pendulum defines the time period of the pendulum. So you will get this value. So it's very simple. It is T is equal to 1.09 seconds. So it's very simple. So you can calculate the time period from here. Now when you calculate the time period, you will put the value of I here and then you will calculate the muzzle velocity. Thank you.